Hello everybody. In this presentation we're going to talk about the classifications of matter and how they are separated depending on what they are geared towards. So the first thing is going to be matter separated by two pieces. First one being mixtures and the other one being pure substances. Now in a mixture we've already talked about that you can create homogeneous mixtures and heterogeneous mixtures. Heterogeneous mixtures are mixtures where basically you can combine two or more substances together where you actually end up with a difference in appearance. While homogeneous mixtures, meaning that same idea, you can go two or more in there, but they're going to be the same. Example of these are it's milk, and then the other one for heterogeneous could be something like water and mud. A pure substance is a little bit different. These can also be separated out by matter can be separated out by physical methods. And these pure substances are broken down into compounds and elements, which could be separated out using chemical means. Now, the difference between these two is that on the pure substances, you do have to break these down using chemical methods or reactions, while in the mixtures, you can use physical means such as evaporation or distillation. Now, the states of matter are broken down to three types: solids, liquids, and gases. As you can see from the picture, a solid basically has more stronger attractions to each other, while a liquid has somewhat in the middle, and gases are generally far apart. And because of these, they retain certain characteristics and properties that allow gases, solids, and liquids to perform differently. Now, the difference between a physical and a chemical change involves that a physical change does not change or alter the composition of the identity of a substance. So in other words, tearing a piece of paper would be considered a physical change. Crumpling it up would be a physical change. You are changing the actual physical appearance, but not necessarily the actual atomic level. The example is going to be ice melting. It still is water, and also sugar dissolving in water, where the sugar still stands in water and is still considered to be a physical change, but not necessarily a chemical change. A chemical change, by contrast, is going to be one that is changing the identity of the substance. And in most chemical reactions, you would end up getting this. And these are really easy to spot because you can't quite go back to its original reactant in certain cases. So the example of this would be hydrogen burning burns in air to form water. So whenever you have hydrogen, you burn it, you are going to form water as a byproduct. The original compound was hydrogen gas, and the output was water. And because of this, you have technically altered it by combining oxygen into hydrogen to create that. Now, the biggest difference I like to say is that you can always go back to its original reactant. However, it requires a little bit more work to do that. Now, going over extensive and intensive properties is another piece of terminology that's generally really applied to matter. The first one being an extensive property. Now, an extensive property is a material that depends on how much matter is being considered. So, for example, if we take a look at mass, that is considered to be an extensive property because depending on how much of that material you have, the more mass it would be. The less mass you would end up with, obviously that would have a lowered mass as well. Length is another example. The longer something is, that also depends on how much matter is being considered. So the more mass you have, the more matter you have, most likely the longer that item is going to be. And same idea with volume. So things that could change depending on the material that you have. In contrast, an intensive property is where the material does not depend on how much matter there is. In this one, you can add as much of that material in there and it will not change that property. And the example of this would be density. The density of water is always going to be the same regardless of how much water you have, whether you have 10 ml or 20 ml or 800 ml. Same thing with temperature. It doesn't really matter in terms of how much matter you have. The temperature or the boiling point of something is always going to be X amount, or the melting point will always be a certain amount. Color will also be as well as another factor. Same idea. Certain substances will always be black, and it doesn't matter if it's going to be 1 gram or 10 grams. Matter is anything that occupies space and also has mass. So if we narrow down the definition of this, this has to do with the idea that mass is a huge property of matter. And so we talk about matter in terms of the units that we're talking about. We're talking about the SI is going to be kilograms. So we're always going to be using kilograms as a way to report out, although we will be using grams in the lab to weigh out things. So 1 kilogram is equal to 1,000 grams, or 1 times 10 to the third power grams. Weight is going to be a little different because weight you're adding in gravity, which increases that by accounting for the force of gravity. Now that's obviously going to change depending what planet you are. And so on Earth, what you need to do is consider that if you multiply the gravity for that, for example, it could be 1.0, you can multiply by the mass to give you the exact weight. And so here we're going to be using 1.0 as that. Obviously in the moon you're going to have a different weight because gravity is less. So 1 kilogram bar will weigh 1 kilogram on Earth, but it's actually going to weigh 0.1 kilogram on the moon, accounting for the weight. However, the mass should not change. All right, so these are the SI units for specifically all the metric stuff in chemistry, and I highly recommend you memorize these. Now for length, it's going to be meter and symbol M. Mass is kg or kilogram. Time is going to be seconds. Electrical current, amperes, is A. Kelvin is going to be temperature, not Celsius or Fahrenheit. Amount of a substance is considered to be mole. And luminous intensity is going to be CD. Now, obviously, we're going to be using grams in most cases, but kilograms is the SI base unit. Now, the prefixes are going to be the same as well during the metric system. It's going to be tera is going to be 10, 10 times 10 to the 12th, giga, 10 to the 9th, mega, 10 to the 6th, kilo, 10 to the 3rd, and then after that, it goes into the negative. So a 10 to the negative 1 would indicate 1 over 10 for a deci, centi would be 10 to the negative 2, milli, 10 to the negative 3, micro, negative 6, negative 9, and so on. All right, so let's talk about some ways in which we can measure certain items. So if I asked you to calculate the density or specifically certain objects, how would you go about doing that? For volume, we'll be using the SI derived unit, which is cubic meter or M3. So if you do have cm, you could obviously have to convert to a metric cube. So 1 centimeter, if you take a look at it, is also the equivalent of 1 ml. 1 centimeter out of this entire cube occupies 10 centimeters. And in 1 liter volumetric flask, you would go ahead and do the calculation. So if I ask you how many cubic, if we have 1 cubic meter, how many meters cubed would that be? And in order to do that, it will be a factor of 1 times 10 to the 3rd power. So what you would do is take that to the 3rd power, which would give you to the 6th. So also 1 decimeter, and so on. So 1 milliliter is equal to 1 centimeter cube based off these results. Now, in terms of density, density is going to be another property that we use to measure intensive properties, and that would be kilograms per M3. And so if you do the calculation for density, it's equal to mass over volume and M over V. And so here's a question that I want you guys to think about. So if you take a look at the units for density, it would be 1 gram over cm cubed, and also 1 gram per ml, which also would indicate 1,000 kilograms over M3. And so you can always do these conversions back and forth. However, if we go ahead and give you something like this, what would be the mass? Okay. All right, so first off, you would have plugged this equation in, so it would be a 21.5 plug-in right here, and then the volume, and then you would go ahead and cross multiply. So the very first step you would do is use D equals M over V, multiply M times D times V, and then plug these numbers in, and they should cancel out the units for cm cubed, which should give you 965. Now notice carefully, this is 3 significant figures because the 21.5 has the lowest amount, and it is a multiplication. All right, for temperature scales and for looking at instrumentations, there are 3 of them, but we'll be using the SI base unit, which is Kelvin. Just to give you a couple of numbers that you should always know, is that on the Celsius, 100 degrees Celsius is considered to be the boiling point. Fahrenheit is considered to be at 212, and then body temperature for Celsius, 3798. And just to give you an idea, freezing point, 273 for Kelvin, 0, and then 32 for Fahrenheit. Conversion for Kelvin is going to be equal to 273.15, adding to the Celsius. which also, here are some important numbers. 273 is equal to 0 degrees Celsius, which is going to be freezing temperature. And if you add that up, you should get 100. For the Fahrenheit conversions, is 9/5 times C plus 32.